Okay, so when we are being asked to relate vapor pressure to vaporization, we've got to remember what the definition of vapor pressure and normal boiling point is. So the normal boiling point occurs when the vapor pressure, so that is the pressure exerted by the gas above the surface of the liquid, is equal to atmospheric pressure. So normal atmospheric pressure is usually equal to 1 atmosphere or 760 torr. Any other units you can convert to bars or whatever. So that's what we're normally looking at, okay? So whenever the pressure above the liquid, the vapor pressure reaches atmospheric pressure is when we reach the boiling point. So there is a proportionality between temperature and vapor pressure. The hotter a liquid is, the higher the vapor pressure above it. More of the particles in that liquid have sufficient kinetic energy to escape from the liquid state into the gaseous state, okay? And that is not a linear relationship, as you can see from the shape of these plots, is an exponential type relationship. So to answer these kind of questions, we're going to look at a plot of vapor pressure against torr. So first of all, which liquid is the most volatile? Well, the most volatile liquid is going to be the one that boils at the lowest temperature. So I can just about, I think, see on my plot here where 760 torr is, excuse my old eyes. So I'm just going to go ahead and draw a line across here. ALEKS actually has a tool that helps you do that. So here is my 760 torr line for atmospheric pressure. So you can see at a lower temperature than anything else, this blue line is going to intercept that purple line for the vapor pressure. So if I drop down where these two intersect as closely as I can, based on what my poor old eyes can read, it's probably a little bit to the right of that, but I'm using crummy drawing tools. So this is going to have the lowest boiling point, whereas the highest boiling point is going to be whatever this one is. So I'm going to drop a line down to here, right? So this is going to be the least volatile, the orthoxylene. Okay, it's going to have a boiling point of, let's see, is that 10? 1, 2, 3, 4, 5, 6, 7, 8. I think there's 10 dashes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so about 140, 1, 2, 3, 4, about 144 degrees Celsius. This one is going to be about 107 point something, right? As good as I can read. Let's go with 107.5 degrees Celsius. So that is going to be the most volatile right there. So let's see, blue line, isobutyl alcohol. Isobutyl alcohol, alcohol. Is going to boil at the lowest temperature, okay? The least volatile will be the orthoxylene. Orthoxylene. Okay, so what else? What is the normal boiling point of each liquid? Well, I've already kind of answered that for two of them. So for the isobutyl alcohol, we have estimated that to be, it says within 1 degree Celsius, so that's okay. So I'm going to say 107.5 for that one. For the orthoxylene, no, sorry, pyrrole. It's asked for pyrrole first. Excuse me. Apparently, I can't see colors. So pyrrole is a black line. That's the one we haven't done yet. So where the 760 torr line meets the black line for our pyrrole, I think that is pretty much spot on 130 degrees Celsius there. So pyrrole is the one in the middle, 130. Orthoxylene, we read off as being about 144, I believe. And then the isobutyl alcohol as 107.5. So obviously, if it was a different altitude, atmospheric pressures could be different, but we're talking normal atmospheric pressure. All right, so suppose a beaker of orthoxylene, okay, so we're looking at the green line, is put inside a sealed tank containing orthoxylene at 136 degrees Celsius and 803 torr. So what I'm going to do is I'm going to change color here. Let's see what's going to show up. I guess pink, why not? So I'm going to draw a line for 136 Celsius, which is going to be 9876, about here to where that intercepts the green line. And let's see. Oh, 803 torr, so that's above atmospheric pressure. I'm going to do it just, yeah, it's pretty much on 800, right? Either way, what you can see is those lines, that point where we're actually at right now, they are intercepting well above, about here, right? Sorry, I was a bit to the right, well above where our vapor pressure line is, okay? So what that's telling us is the pressure is higher under these conditions than the normal vapor pressure. So in order to sort of get back to equilibrium, what this system is going to want to do is it's going to want to get back to here. So how is it going to do that? How is it going to lower the pressure? Well, that would tell me that some of the gas is going to have to condense back into liquid, okay, until we reach the equilibrium situation again. If the opposite was true, if we'd ended up down here somewhere, then we would have to have some of the liquid evaporate into gas to increase the vapor pressure to get back to that green line. But that's not what we're looking at under these conditions. So will there be more liquid in the beaker, less liquid, or the same amount? If it was the same amount, we'd be right on the line, right? So in this particular case, I should probably give you some notes on that, right? So pressure too high at this point. So our gas will condense to lower the pressure. If the gas is condensing, so we're going to end up with more liquid in that case. I can't spell. So the amount of liquid in the beaker, we're going to check the more box. Okay, so that is all you have to do with those kind of questions. Okay, so to work out the boiling point, look at where the vapor pressure line intercepts that 760 torr line, drop a line down to read off the temperature. Lower boiling point in terms of degrees Celsius means more volatile. Higher boiling point means less volatile, okay? If the system is moved away from equilibrium, it follows Le Chatelier's principle, okay? So if our vapor pressure is too high, we got to reduce pressure. How are we going to reduce pressure? Gas will condense into liquid. If our vapor pressure is too low, then we're going to have to increase the amount of gas. So liquid will evaporate into gas. If we're right on the line, no change. All right, I think that's all you need to know. Hopefully that helps.